Okay, so next up we're going to be working on the chain rule from section 11.5 for multivariable functions. And you should be familiar with chain rules kind of from Calculus 1. If you wanted to take the derivative with respect to x of some f of g of x, then you take the derivative of f and keep g inside, and then you multiply by the derivative of g. And so you're used to this idea that kind of if you have multiple dependencies of a function, you can deal with that by taking products of derivatives. But in the context of Calc 3, we don't just have things like g of x, f of x. Maybe not have so many colons in one line. So we've been dealing with things like z equals f of xy. So for example, z equal to x squared plus y squared. And so more than just f of x, we're dealing with f of xy. Z depends on two different variables, and we've been learning about partial derivatives. But then going even further back in things we've covered, we did sort of parametric definitions of the x and y components of vectors. So it should be natural to think about x is a variable in z, but maybe x could also be given by some function that depends on t time. And y could be the same. And so if you wanted to take the derivative of z with respect to time, you'd wonder what that is. And real quick, we could go ahead and just plug it in. We could say z equals x squared plus y squared. Let's say x is equal to 2t plus 1, y is equal to minus t. So then that would become 2t plus 1 squared plus minus t squared. And then we could take a derivative. But we'd like to do something easier than that. Just like the chain rule helped us sometimes take easier derivatives than maybe like factoring out something to the 8th power. When we learn the chain rule for z depending on t in this sort of situation, we could be saving ourselves some time. And what we're going to need are some graphical tools that help us find new chain rules. Graphical is even kind of the wrong word because you might think we're doing graphs. Really, they're sort of diagrams. And the reason we're going to do this is because you may have noticed at this point in all the calculus we've been doing, it's really hard to keep track of all these dependencies that we introduce, all these different functions. Z depends on x and y, x depends on t, so on and so forth. And so these diagrams are going to help us keep all those things in an orderly fashion. So they're just going to help us keep everything organized in our problems. So if we have something like z equal to f of xy, we're going to represent it as we have z, and it depends on x, and it depends on y. If we have x equal to g of t, y equal to h of t, we're going to represent that with more lines and boxes. We'll say, okay, x goes down to t, and so does y go down to t. And if you would prefer to do this sort of like so that they both depend on the same t, that's fine too. Whichever way you prefer to make the diagram is okay, as long as you have an arrow pointing kind of between boxes that represent the inputs to a function that give you the output variable at the top and the inputs in the layer below. And I'll write in words what I just said, but I thought showing a picture might be clearer than the verbal description. So what you're going to be doing is putting dependent variables So for example, z is dependent on x and y. Above their independent variables, and I'm going to put independent variable in quotes because even though as far as z is concerned, maybe x and y seem independent, actually x depends on t, y depends on t. So we'll say, maybe we'll call these input arguments. And then we just connect those with lines. And we're just going to keep going until we run out of variables. That's the general idea of how we're going to build the maps that help us find chain rules. I'm going to go ahead and stop here. In the next video, I'll actually write out like steps numbered so that you know how to find the chain rule at the end of building this diagram. But I don't want this video to go too long.